So the topic here today is predicting students' final grades using machine learning method with online course data. So from the title, we can see basically the objectives of the chapter is how we can predict student learning using machine learning. So I don't have slide, but all the talks is here on our studio in this format. So the goal of this chapter is to explore using machine learning to answer questions with respect to teaching, learning, and educational systems. So that is basically the goal of the chapter. So we're going to look at what machine learning is, how can we use machine learning algorithm to determine student final grade, the factors, the motivation factor that student got a final grade, what determine those grades. And here are the basic background of what we're going to be doing is that we're going to examine the educational success in terms of student interaction with online science course. So basically the data we are going to use is from online course delivery, and we're going to determine the success of students based on their interaction. The data includes self-reported motivations as well as behavioral traits to identify predictors of final course grade. So what are the motivation that student got a final grade? Also behavioral traits. And these are some of the questions that we may answer at the end of these. Is motivation more predictive of course grade as compared to other online indicators? So this question is telling us about, is motivation more predictive of course grade? If a student is motivated toward a course, does he got a better grade? We'll see this at the end of the chapter. And if not, which types of motivation are most predictive? So if we have many kind of motivation the student has toward a particular course, now which one is more predictive toward the achievement? And which type of traits measure is also predictive? And how does random forest compare to linear regression? So these are 4 things that we aim to see at the end of the chapter. So the data set is basically, as we said, is based on a line management system, discussion forum, academic achievement data measured by final course grade. And the students are 499 students that we're going to see to determine their motivation. And what we're going to look at here is we're going to look at what is called complex problems. So there is what is called simple problem and complex problem. So a simple problem is one that actually have one-to-one relationship that determine simple linear relationship. For example, if we want to tackle simple problem, we could choose just one of the relationship, saying motivation. If a student has a motivation, then he can have a higher grade. But what we are not interested of this simple linear relationship, we need a complex relationship where we have different motivation factors that can have a student have a higher grade. And to explore this, we're going to use machine learning. So that's bring us to what machine learning is. So machine learning is basically used to perform predictive tasks. And nowadays, there are many terms, machine learning, predictive analytics, they are more or less the same. But predictive analytics is somehow used historical and current data to make predictions, while machine learning is use current data to train models and algorithms and can be supervised and unsupervised. So having a look at the motivation, what we want to look at, basically we want to use machine learning algorithm to predict student performance. What are the factors that get students to have higher grades? And we said one way to do that is using machine learning, and machine learning is used to make prediction. So there are many kind of algorithms for machine learning. For this chapter, the machine learning algorithm that's going to be used is called random forest. So why random forest? So random forest is well suited for nonlinear modeling. As we said here, we're going to use a complex relationship where we do not have a kind of linear relationship between one-to-one. So random forest is suited for that because we have many parameters, motivation, engagement, achievement, many parameters that we're going to use, and random forest is suited for that. As you can see, we have 11 predictors. So, and we have only one outcome. So what we mean by outcome and predictors, predictors are the parameters or variables that actually, when we do modeling, that serve as the predictor of the outcome. So we usually have a single sometime outcome and many predictors. So here we have the problem, we have 11 predictors and one outcome. And also in this kind of case, if we use traditional linear models, it may not have quite good performance if you have this kind of nonlinear modeling. So as we see in the last part where we compare linear regression and random forest performance. So let's dive into the code and see what this is all about. So to recap what we have said, what we're going to do is to use a popular machine learning algorithm called random forest to perform predictive tasks of student grade from online course. And here we load our libraries where we have the cohort package, which is used to make modeling, and it includes random forest and many other machine learning algorithms. Here we load our data sets where we have these data. So our data is from here, as we all know from the chapter. And here we use the glimpse function to look at how many variables we have. So here the data has 606 rows and we have 74 columns. But this data is enormous. We have 74 variables, and in machine learning, not all variables that you were given in your data may not be useful. So in this case, we may actually drop some of the variable and pick a predictive variable that have related performance to our algorithm. Okay, all these one are variables in the data 74. So here we said it is generally good practice to select, excuse me. Okay, it is generally good practice to select few variables you are interested and do modeling with them only. So as you can see here, we have 74 variables. So here we'll select only few variables that we are interested to do our modeling tasks. So here we select few variables here. We have int, UV, PC, and here, as you can see here, we have 14 variables that we have selected, and we have 606 columns. And what are these variables? So these are the variables. So the outcome variable we want to predict is called final grade. And the predictors variable, 11 predictors we have, these are them. We have init, which is the interest in the course. What is the interest of the course student have? Does this have large interest or small interest? Perceived utility value of the course, perceived competence for the subject. All of these are motivation predictors variable. We also have many other variables here, and in all we have 11 predictors. So this problem, we are going to use a single outcome variable and 11 predictors. Now, having looked at the data set now we have, before any machine learning task, we use what is called feature engineering or pre-processing. Feature engineering or pre-processing allow us to pre-process or clean our data, put it in a format that is suitable for machine learning algorithm. Because often data comes in format that is not ready for machine learning. Therefore, we need to do what feature engineering, change some stuff, and when it is ready, then we send the data give the data to machine learning algorithm. So at this section, have a look at the data. We have one outcome variable and 11 predictors variable. We are not going to just use the data as is to feed into machine learning algorithm. What we're going to do is we'll do what is called feature engineering, clear the data, make it suitable for machine learning algorithm. One of the example here is that random forest algorithm does not accept cases with missing data. So if we have a data that is that has a missing variables and you feed it into random forest algorithm, you may not get a good performance. In such case, you need to perform what is called feature engineering, whereby you can omit or remove features that are missing in your data. So also, if you have a small data set with a lot of missing feature, that may not be good candidate to use with a random forest algorithm, because you need to remove all the missing variable, missing data from the data set. So as we can see here, our data here, we have 606 columns, variables, rows, and we want to try to remove missing values. So here we can see we use this function na.omit df. Now here we remove. So we are going to use only 464 records from the data set from 606. So here, that is, we have done one step in feature engineering. The next step is removing some variable. At some point, some variable, if you have a data, they may not have some kind of any predictive power. They may affect the performance of your algorithm. In such case, when you are given your data, you may remove those kind of variables, or you may do some kind of feature engineering. Sometimes you may have 3 variables that you can put together to make them into a single variable. That is part of feature engineering. So here, sometimes will not be, you may have variables that are highly correlated, and this is a problem to modeling tasks. Also, some variable, they have no variability. So if a variable does not have any variability in your data, we tend to remove them from our data. So in this particular example, we have one variable that does not have any variability in our data set. So to check if in your data there is a variable with no variability, we use this near zero var. So here is our data frame, and now we run this. When you see, as you can see here, zero variability is false, zero variability is false. But here, when we come to this variable, zero variability is true. It means this variable, enrollment status, it will not be useful in modeling tasks. It will not be useful in modeling tasks. So we need to remove it from our data set. So looking at this variable enrollment status, we can see that we have 464. But what it is interesting is that all the value of these 464 are approved or enrolled. So they are not changing at all. They are the same, constant. So if you have a particular variable that is always constant, it means it will not have any effect in your modeling task. So we can remove it. So in this case, we can remove this enrollment status from our data set. So here, as you can see, df select minus enrollment status, we drop this variable from our data set. So also you can check your data set if you have high correlation or multicollinearity, and you can remove or deal with this issue. But in this example, what we deal with is the problem of non-variability. So this is all part of what we call feature engineering. The next one is changing categorical variable to factor. So in modeling in R, if you have a character variable, it is always good to change it to a factor. So that is a factor. They are always default data type that are used in R for modeling tasks. So if we look at this data set, some variables, they are actually categorical variables, so we can change them. So here This here we change the all variable that are character variable to factors. So we have seen now the future engineering. The next one, what we are going to see is called data splitting. So data splitting allow us in machine learning to first, before we do training, we need to split or divide our data set into what is called trends and test sets. So the trend set is used to train your machine learning algorithm, and the test set is used to see whether your algorithm is performing good on seen data. So we're going to do that now to divide our data set. But what we are going to do is we want to split our data based on the outcome. So the outcome here is the final grade. But one thing we want to do here is that we want to do random partition based on our final grade. Because if we by chance partition our data and it turns out that one part has final grade with higher accuracy and the one part has final grade with lower performance, and one partition has higher performance and another partition has lower performance. So we can see here, this partition is not actually balanced. So we need to have a kind of partition where we have balanced partition, where we have equal representatives of final grade. So that is why we say we want to split the data based on outcomes. So this function create partition is used to create a data set, create a partition of the data. So here we can see this is our data frame, final grade. We create a partition 80%. So here we said trend index here, we create a new variable 80%, and we create now partition which is 80% of the data. And now we use this variable to create a trend set and test set. So here we can say we have a variable df trend set, which is 80%. We have a data frame for training set, and the remaining part here, which is 20%, will be a test set. So this is basically a way to partition your data into 80. Sometimes this is a rule. We divide our test data, our training data into 80-20. So 80 will be for training set and 20 will be for test set. So here, the training set will have 80% of the data, and the test set we have the 20% of the data. And it turns out that these train set, the outcomes will now be randomly partitioned. It will not have some kind of undesired outcome that we don't need. So finally, after you divide your data sets into train and test set, what you need to do is to train your model. So basically, as we said, what we are going to do is we're going to use what is called random forest machine learning algorithm to train the data set. So here we set seed. So as we know already, setting a seed allows us to replicate our machine learning tasks, whereby for reproducibility, if I run a particular task, one of my friends can rerun the something and can have the same result. So this is basically the way to specify how to train your model. This is a function train. The first thing here, we need to provide the data set. Final grade is the outcome. And here we use this formula, and dash here, it means all the predictors. And here we need to provide the data, which is data frame train. And now here we need to provide the method we want to train our algorithm. So the method we want to use is called RANJA, which is random forest algorithm that is used to train, to do modeling. So having specified this, we run it, and we can see that having run this, we can see this is the results. So we can see here we have some kind of M-try, split root, RMSE, R-squared, MAE. And what we are interested here is to have RMSE small n high r squared. So as we can see here, the last part, which is using m try 19, and split rule is extra 3, and RMSE is 13.4, and the last one, R squared, is this, is what actually have the beta performance. So these m try split roots, they are kind of specific to random forest algorithms. They are called tuning parameters, and we can actually tune them or modify them so that we give the tuning parameters we want. Here in this case, we do not provide any tuning parameters. We allow the random forest algorithm to train this data, to train on this data without any fine tuning based on the baseline. So here, based on the baseline, tuning parameter minimum node was held constant at value of 5, and RMSE was used to select the optimal model using the smallest value. So this is the one that interests us. So here, as you can see, we are looking to minimize the root mean squared and maximize the variance explained squared. So this is, we will always be looking at where the RMSE is lower, where this is higher, which is finally this case. However, we can tune these parameters to our need so that we can have better accuracy. So when we tune the parameters, we can have better accuracy. So these are some of the tuning parameters: M-try, split rule, minimize nodes. We can provide this. These are some of the theoretical part of random forest, but for the sake of this chapter, they are just called tuning parameters, and they allows you to actually provide more parameters to make your machine learning algorithm perform better. So in this case, as you can see, we can provide some tuning parameters in some ways. You can see we can use repeated CB, trend control, and we provide here trend control here after specifying this one here, and the performance now increased from the previous one. As you can see here, the RMSE now is 12.5 instead of for the previous case, which is 13. And we can see here, so basically the random forest algorithm has many tuning parameters that you can provide and increase the performance of your algorithm. Not also that we can provide these tuning parameters as well here. We can use tune grid here using expand grid function. We can provide the M-try here, the one we want, not the default one. Here we specify M-try. And you can see we use split rule, variance, extra trees, and minimum node here we use 1, 5, 10, 15, 20. So by default, it's used, the minimum node size is 5. And by default, the M-try is changes randomly, but here we specify and we train this model again, and it can give us better performance as well. Any question? Yeah, so does anyone have any preferred resources on future engineering? So yeah, the future engineering, there is a book, Future Engineering, by the author of cohort package. What the name of this book? What is name?
By the author of what?
Cohort package. What is name? Future engineering. Max, yeah, Max. Yeah, I think this is Max, Future Engineering. This is the book. Let me share. He has a good book on future engineering, and yeah. So this is the book, Future Engineering, and it discusses a lot of, specifically a lot of future engineering techniques for machine learning. So it's a good read for that.
Thank you. I was trying to do a little on some data similar to this, but I have no idea what the rules of it are. I just manually combining some columns and weighting them differently and things. And it seemed
Oh,
like there
yeah.
were underlying rules, but I didn't know.
Yeah, so as you can see, the book is quite comprehensive, and yeah, it basically talks about the future engineering. Right. Okay, so
yeah. Can I ask, with these tuning parameters, is there any sense of like strategy to this, or is it really just
yes,
throwing a lot of different
so
parameters
that
at the
is
wall?
what, yeah, so I think that is why it's called tuning parameters. You don't know what will work. So basically you just provide to the algorithm different kind of parameters and try to allow the algorithm to use all those parameters and pick the best case scenario from them. Yeah, so I'm not quite sure because if you look at this in here, the first one we have seen here, there isn't any tuning parameters. It just by default settings, the random forest will train the model. But if you need more accuracy, you want your algorithm to perform better, then you can try to go from normal settings to try to tune the model. When we say to tune, is to like to try to make it better by providing some kind of tricks. So every algorithm has its own specific parameters. So this random forest, it does have these parameters like mtry, split rule, which are specific to random forests. I think the extra trees, the variants, they are specific to also random forests. I'm not quite sure for now. What does that mean? It goes to the theory of random forest and tree, where maybe how far you have gone with it, because random forest is basically based on tree implementation, I think, iterative search. Yeah. So, yeah, so, okay. So having now trained your model on training set, the next thing you can do is to do prediction. So how can we do prediction? So we do training on a training set, and to see whether your algorithm that you train works well or is performing as expected, we may want to use test set to try and find out the performance of our algorithm. So as you can see here, this is our test data that we have already created in the first instance. Yeah, this is the test data. We now want to try and see whether our algorithm works well. So let's go on. So here you can see what we want to do is we want to create a new column where we have, so for us to use prediction on the test data, we use a function called predict function. And the first argument is our model, is our what we train on. So if you look at this one here, so I'm using the first one, yeah, this one. So you can see here, RF fit one, we fit our model here. This is the RF fit one. We fit our training data, and I save it here. And now here, when you want to do prediction, all we want to do is, for us to get a prediction, all we want to use is to use the predict function and provide the first argument that what we fit on the training data. And now the second argument provide the test data. That is how you make prediction. And the result is now a prediction. So now what we want to do now is we want to create, compare the prediction and the original observation of the final grade. So here we create a new variable called prediction, and all the prediction will be in the predict, and here observation is the final grade of the student. So what we are trying to predict, if you remember here, we are trying to predict the final grade of students. So we want to compare the value of the prediction and the original observation. And now we create we create a new variable here in our data set, as you can see here. So if you look at this one here, this is the original data set, as we have seen. The data set, look at the last column is n, but here we make a prediction and store in a new pre, and also we stored a variable in observation, that is the observation. So if you look at it here, this is the prediction, and this is the observation, the original grade of the students. So if you look at the here, this is the observation and 3, the final grade, and this is the prediction as a 3. This is the observation, this is the prediction. This is the observation, this is prediction. So you can see the random forest algorithm here is not doing bad, right? Yeah, and it's not doing bad, and we can see that the prediction is somehow close to that. As you can see here, this is the observation of the student grade, and this is the prediction. And yeah, so something like that. This is basically the prediction on that. So now here we want to calculate the RMSE and also the R squared. So here we use this function default summary, and we can see that this is the RMSE and this is the R squared. So as you can see here, the RMSE is 13.009, and what can we say about this? This unseen data, we have the RMSE of 13.009. What about the trained data? What is the RMSE there? Which one is better? So if you go back here to our training data, I think this is in here, right? It's 12.9, which is almost 13 as well. We can see that the algorithm is quite doing somehow well also in the test data. It's not that bad as well. So we can see that the RMSE value is about the same when we use the model on test data as it was on the training data. So it's not quite bad. So also the R squared, if we look at it back, is somehow close to when we use on the training data. So this is the results of the prediction on test data and training data. Any question before we continue? Yeah, so Max, he is prolific. Yeah, he is also currently writing the tidy models, and he is heading, I think, the tidy models from Art Studio, which they are basically the current, the way here we are doing the modeling here. Now using tidy models is maybe now the new way to do modeling than this current package. Yeah, and they are actually actively involved and doing working on tidy modeling. Julius Lige and Max, they are actively involved working on tidy model, and the future of modeling in R is tidy modeling. So yeah, the future of modeling in R is tidy model, because even Max is not working currently more on the current package. They are working on this tidy modeling. So yeah.
Did he do the other one independently and then RStudio hired him?
Yeah, sure.
To bring it into the tidyverse?
Yeah,
or
yeah, yeah. So one of his book, Predictive Modeling. Do you know the book?
No.
One of his pioneer, one of the best book, Predictive Modeling in R. If you go in Predictive Modeling, have you seen it?
Is that's not the one you shared initially?
No. Predictive Modeling, Max. Yeah, Applied Predictive Modeling. So this is one of the good book in modeling. No, okay, I share wrong link. Apply predictive modeling. So I suggest one, if you want to start doing modeling, one should start with this Bovee book. It gives the background of what the random forests are, the theoretical concept behind these tuning parameters and everything. So yeah, the current packet is discussed there extensively. Right. So the last part of this chapter is what we call variable importance. So here, as we can see, one of the objectives of this chapter is to predict the student grade. As we can see now, we have do the prediction of student grade using test on-scene data, that is test data, and we can see that the random forest algorithm is doing quite good. Another question that we may want to answer is among these variables, which one is the which one contributed strongly to prediction? Because we have many variables. We have 11, I guess, right? 11 variables. And so which one contributed most strongly to the prediction of the model? That is what we're going to see here. Using another function, this is exactly what we did before, but there is a function called variable importance. When you call the fitted model with this function variable importance, it will shows you what the order of the variable. So if you look at this one here, these are the important variable importance. So one of the main variable that contributed toward the prediction is n. Then subject this, then time spent on a particular course. So time spent on a particular course yields to the grade performance. So if you spend many time on particular course, then your grade will increase because maybe you will understand it much better. So what is this n? What is this n? As you can see here, it's 100. So this variable importance, all measures of importance are scaled to have maximum value of 100. So all the importance here, they are scaled to have 1. So n is having 100% importance. So it is absolutely one of the most important factor that actually contribute toward the prediction of student grade. We have also subject FRSE, which also has some kind of 20%, and we have the time spent, which is 15, and these are some other variables that contributed toward the. We can have subject this, which is 0, 0. The n variable here, I don't know which one is this, n, let's see. N, what is the meaning of n? Let's go back and see what the meaning of n that actually have this n, and what is n? N. Okay. Okay, the number of discussion board posts in total. Okay, so the number of discussion board posts in total. So I think what they mean by this is that if we have a particular course, because if we have a course and that course, there are a lot of discussion in the board, this means that students are engaged with the course. They are trying to understand, to ask questions. So if we have a particular course with messages or posts in the blog, maybe 100 or 200, then compared to another one with just 2 or 3 posts in blog, then that means the one with higher posts, it means students actively involved in the course. They are asking questions, they want to try hard to understand the subject. So these are the importance. So here we can use this, we can plot the variable importance here, as you can see. So here the n is the one that has higher importance and stuff like that. So finally, we want to compare the random forest to regression algorithm. So as we said previously, one of the aim of this chapter is to compare the random forest and regression and see which one performs best. We should know also that this kind of problem we are trying to use, this kind of thing that we are trying to use is actually complex problem, is in the sense that it's not kind of linear relationship. So we do not expect linear regression to work better than random forest. So what do we want to do? So here we have, we fit our method linear model. So here we have LM fit, we have train, the final grade, which is the outcome. And here we mean all variable. Then we provide our data, which is data frame, our train data, which we create here, and which the method is LM, which is linear regression. Then we make predictions as we did in the previous case. We create our observation is the final grade, and we use prediction. We create a prediction, and using predict, we provide the fit method, fit, and we provide the train data set here. The train LM. So here we can see we have the prediction and observation. So here we fit using linear model. So here we 93, this is the observation, this is the prediction 85. Here 81, this is 50. You can see here linear model does not perform well compared to random forest. You can see here 81, 84, and so here also you can see, as we have already did this one using random forest. If you look at this one here, this is a fit for random forest we have already created, and this is the train, and this is the observation, which already we have. When we fitted that one, then we have prediction. You can see that with random forest we have the observation 93, we have prediction 90. So in this case we can see that random forest and linear model do have different performance, and random forest outperform linear model. So here we can use this function default summary to get the RMSE and R squared. So here using the linear model, it is 14.4, the RMSE, but using random forest, the RMSE is 6.02. So we can see always what we want to have the RMSE, small RMSE, but higher R squared. This is telling us that the random forest outperform the linear model, which we already expect to do that. So this is the last bit of the chapter. I think that is all we have. So if you have any question, yeah. All right. So if you have a question, then we can. This is the last part of the chapter.
I'm curious about what contexts, if any, people are using this algorithm in education. Have you guys used it elsewhere, or other machine learning algorithms?
Yeah, which one, the random forest or?
Yeah, the random forest, or any related sorts of things.
Yeah, so I think I don't know, one of the reasons why the authors choose random forest, because it's powerful machine learning algorithms. Mm-hmm. So random forest perform quite good even in Kaggle, in competitions and stuff like that, not only in educational purpose, but in machine learning. In general, the machine learning random forest algorithm is quite good, and you can use both classification and regression with it. Here, as we can see, we are doing some kind of regression tags, but you can use random forest to do classification, to classify something into A or B, some stuff like that. So you can see here, we answer some of how does random forest compare to simple linear model, that is regression. So we can see random forest outperform linear regression model. Which type of motivation are most predictive of achievement? That is the end we have seen. Yeah. So any question? Yeah. Log variable importance, easy for others to understand. Yeah, variable importance is quite good. It shows us what actually contributed to the prediction in our experiment. Right.